what appealed to me about math in the first place. In middle school, high school, I really loved math. That was my favorite subject. And I think because there was just really a very step-by-step approach, and you solved a problem and there was an answer. And I really liked that about math in general. And then as I got into college and got more exposed to engineering, kind of the same process. You can follow a really organized approach and come to an answer or come to a design that meets a specific set of needs. And I've always liked that, as long as I can remember, even back when I was younger. And I think that really drew me to engineering. I also like to build things and create things. I'm not very good at arts and crafts, but I am good at, building things out of Legos, Connects, things like that. I always enjoyed that type of thing, being creative and making fun shapes and projects out of, basic materials.
Yeah, so like kind of as a childhood interest. That's really cool. So, what makes you excited to go to work every day? And what's the most rewarding part of your job?
I love teaching the next generation of engineers. So I love meeting my new students every year and working with them throughout their time. I teach some classes that freshmen take, all the way up to classes that juniors take. And so I really like to see the students go, from their first year where they're just learning, getting to campus and everything's new, all the way through junior, senior year when they're about to graduate, and just really see that growth. I love that. I also really like my job because I get to design new things for the students to work on. So I get to do fun projects myself when I'm trying to figure out what I want my students to do. And I get to design kind of the learning experience too. So how are they going to go about that project? So I think for me, it's a really creative job, even though it might not seem like it. I have to come up with new things for the students to do and new ways for them to do it. And I get to try it myself, which I think is really fun.
Wow, that's really cool. And what is the biggest surprise about being a woman in STEM, maybe before you were a professor, but just kind of learning about the field, or just as a woman, being in your class, teaching it?
I think the most surprising thing to me early on was how few women there were in high school, especially. I was in Science Olympiad, like City. I was in, the robotics team, like Sonia. So I did a lot of that type of stuff. And almost all the people on my high school team were female. I had a almost all girl team of Science Olympiad. I think we had one male team member, and our robotics was about 50-50. And then I got to college, and I think there was only one other female student in aerospace engineering out of a class of about 60. So it actually was really surprising to me. I knew we were in the minority, but I didn't know that we were that much in the minority. And when I started college in 2005, there really just weren't very many of us. And it was a shock coming from high school where I had so many other female STEM friends, and then, got to college and I thought, wow, it's all male guy, all guys here in my class with me. And it was just very different. They were all very nice, all very respectful. It was just a really different environment than what I was used to from high school, where I think, maybe we just had a higher number of girls at my school that were interested, or maybe I just gravitated to that group of friends. But when I got to college, it seemed like it really dropped off in numbers. So it was interesting.
Yeah, did you see the difference when you were teaching the classes? Like over the years, did you see more and more women join, or was it kind of like stagnating and you're just cheering the women on in your class because you're just hoping for more people to join?
In mechanical, I feel like we have a kind of a growing female student population. In aerospace, I think it just kind of goes up and down. Aerospace in general, a lot of people are interested in that area, or some people aren't. And so it just kind of, I think, goes up and down year by year. Even our overall numbers will have more students one year and then less, fewer students the next year. I think just as interests change and grow. So it's kind of been the same with the female students there too. But in mechanical, I've really seen an upward trend as a professor.
Awesome. So, and what's something you wish you knew before you went into STEM, or before you became a professor for women in STEM, or all students?
I think that you don't have to know exactly what you want to do when you start, would be kind of my piece of advice, or something I wish I knew. A lot of people that I started school with, I felt like they had found their life passion. They always wanted to design cars ever since they were 3 years old. They knew that car design was what they wanted to do, and I didn't really feel that. And so I sometimes felt like maybe I wasn't in the right field if I hadn't found my life's passion. As I was able to try different things, I was able to try aerospace and math and kind of this more biomedical project. I was able to find what I like to do. And so for me, really enjoying problem solving was enough. And then I was able to find what I wanted to do within that. So I think I wish I knew that I didn't have to have an idea of what I do right away. I could figure that out over time. And in my case, even over 8 to 10 years while I was in undergraduate and grad school. You can
Wow.
change your mind.
Yeah, it really is that flexible. Wow. Now, where the best part about this is that you can ask questions as our audience. You can ask Dr. Schmidt any question that you want. You can send it to the chat if you don't feel comfortable, saying out loud to the group. And we're just gonna be sitting back, and when we get a question, we'll just say it out loud and begin the question asking.
Come on, someone has to ask a question. Again, if you don't feel comfortable like actually asking it, you can either message Sonia or I privately and we can ask, or you can just put it in the chat.
Cool. So we have a question. What other jobs besides teaching do aerospace engineers do? Question mark.
Yeah, so a lot of our students, so the students that I've had in my aerospace classes, go on to work for companies like Boeing, designing planes or other aircraft type structures. I have some students who have gone on to work for national labs, researching, for people who are designing for space. I know some students who've gone on to work for NASA or SpaceX to design rockets or to design satellites to be deployed into space. Sometimes even aerospace engineers leave the field a little bit. So I know some who've gone on to work for sports companies. They know a lot about forces on things traveling through air. So maybe they could help design race cars or new types of sporting equipment like bike helmets to be more aerodynamics and things like aerodynamic and things like that. So a lot of different careers you can have, but most of our students go on to work in the design or research field for aircraft like airplanes or spacecraft like satellites or rockets.
Wow, that's amazing. I didn't even think about like helmets and stuff, how you would have to have experience in that field before going into designing something like that. Wow.
We got another question. How do you get into STEM at an early age, especially when a lot of people in those areas are not like you?
I think for me, one of the things that got me into STEM as early as I did was joining things like math club or science Olympiad or any of those extracurricular programs that my school had. I joined as a student. I made a lot of friends through that, which I think helped me, as I went along. So I kind of started those programs in middle school or early high school. And then some of those people developed into my closest friends. I didn't know them before I met them in math club or before I met them in Science Olympiad, but by the time we graduated high school, we were friends for life. They're people I still talk to today. So I think talking to any of your teachers about what opportunities your school has, and if they could recommend you for that club or help you get connected with that club, that's a great way to get started. Or even programs like at your local science museum or any sort of science centers. those are great too. I lived in kind of a small town that didn't really have that, but I think if you're in the St. Louis area, especially, you have some more options.
Yeah, I think even at Clayton High School, we have like a rocketry club, right, Sydney? Pretty cool. There's a lot of different options, especially in the St. Louis area at the Science Center. There's a lot of cool activities you can join or clubs you can do, or you can start your own club. That's always an option too.
Yeah.
Yeah, I always gather a couple friends and talk them into doing something with you and found a club. That's always a good way to go.
Yeah, you only need 4 people, according to, well, at least in our school's form, you only need 4 founding members to join a club. So I encourage you guys to go do that if you feel passionate. Open for a few more questions. Ooh, okay, so we have another question. What are the daily responsibilities of an aerospace engineer? Or just like, you know, in the field?
Yeah, so I guess it really depends on what type of job you're working in, and aerospace engineers can do many things. So I mean, I studied engineering, aerospace engineering, that's my degree, but actually what I do every day is teach. It probably doesn't look too different than what your teachers in high school or middle school do, but just at a higher level. So I teach all day, pretty much every day. That's what I do, and I design new teaching activities and I grade student work. So my job is very similar to a typical teaching job. I just focus on aerospace engineering. If you were to go into the industry, like if you were working for Boeing designing a plane, your work could consist of modeling, like doing simulations, which is kind of what we're going to do here in the activity. So writing simulations for different parts of the plane. It could include working with people on manufacturing, so working with people actually building the parts of the plane to get exactly what you need, where you need it. It could include design work, testing parts. You could be out testing a new part of a plane. You could be, you could be out there, I guess, taking experiments. So you could have something in a wind tunnel, which we'll talk about here in a little bit. You could be measuring forces on a wing in a wind tunnel. If you were working for a satellite company, maybe you're working in communications, testing out your satellite communications, all kinds of different things depending on what you'd work in. But typically, some combination of modeling and experiments go into most aerospace engineering projects.
We got a question asking if there are many other, are there many other female faculty members?
In our department, there's just one other in aerospace and mechanical. I do have a fair number of female faculty friends because our university really supports the female faculty, and we actually have a group on campus called Female Faculty Fellowship Forum. I can't remember what the last female faculty group. And so we get together the female faculty from all the departments. So I've met people in mining, in civil engineering, in chemical engineering, and then even in like psychology and English, so non-engineering fields. And that's been great to have kind of a support system here at the university. Since there is only one other person in my department, they've helped connect us around the whole university.
So if you guys are good on questions, we can move on to the simulation activity. If everyone's okay with that, any final questions? And if not, we'll just move on.
All right, if you guys don't see anything else, if you want to unshare your screen so I can share my screen, I can bring up just a couple slides here. Awesome. So let's see here. Can you guys see the slides that I've got up? All right, awesome. So one of the classes that I teach regularly, I teach it every fall, is called Aerodynamics. And so the activity that we're going to do today relates a little bit to that class. And so when we say the word aerodynamics, maybe you think about something being aerodynamic, something cutting through the air really nice, but the term in general just means the study of the property of moving air and the studies of the interaction with that air and a body that's moving through it. So maybe how a plane would move through the air, or how a race car would move through the air. We want to study the forces on that object by the air and try to optimize our design to make that as efficient as possible. And so typically the goal when you're studying aerodynamics is to model with math or measure with experiments the aerodynamic forces on an object. So the forces that the air puts on that object. So for example, like the wing of an airplane, you could study the aerodynamic forces on a car, a bike helmet, or the whole cyclist. There's some places where people will test out their entire cyclist and bike setup in a wind tunnel. So, study how the air puts forces on that and how we can optimize that so the person or the plane or the baseball can cut through the air really smoothly. And so when we talk about an airplane, which is what we study most in our class, what we're looking at is what keeps it up in the air, and what slows it down, what's going to make it need more fuel to go, say, from St. Louis to the East Coast. And so the way we study this is with a wind tunnel. So we'll do some math and some simulation here at the end, but another way we can study this, and that we do in my course, is with a wind tunnel, where we can put a small scale object like a wing or a really small scale version of the airplane inside a tunnel and flow air past it really quickly. And so we have a wind tunnel that looks something like this. It's just kind of a schematic here, but we actually pull in air from the ceiling way up at the top. We run it through a bunch of different kind of honeycomb and screens and stuff to smooth out that air so it's not all crazy and bouncing around. It's just nice, straight, smooth air flowing through. We run it through this little nozzle section past whatever we're testing in our test section, and then back out through the ceiling. And so we can put different pieces in there. We could put a model of a plane, a model of just a wing itself, or we even have models of baseballs, golf balls, things like that. We can put in that test section and study the forces on it. So we can have little force probes, basically like little scales, and see how much lift and how much drag, which we'll talk about here in a minute, are put on those objects. And so let's say we've got a plane in there. Our plane has four main forces on it. It's got the weight acting down. The plane is a very heavy object and it wants to fall back to Earth. It has the thrust due to the engines moving it forward. But then it has two aerodynamic forces, the lift, which opposes the weight. So it's perpendicular to that plane motion. It wants to keep the plane in the air. And the drag, which opposes that thrust or opposes the plane motion and wants to kind of pull it backwards. So it wants to slow the plane down. And typically when we're designing or when we're studying in the wind tunnel, we want to maximize the lift because then we can fly a heavier object if needed. And we want to minimize the drag. We want to have as low an air resistance as possible so we don't need as much fuel and we can be more efficient in our flight. And we've been able to improve the aerodynamics of aircraft over time so that they're more fuel efficient and can go farther with less. And less fuel means less weight. And so it's just kind of a feedback process. If we can have a lighter plane, we can do more things, carry more people for one. So if we think a little bit about the factors that affect lift and drag, the speed that the plane is going, or in the wind tunnel, the speed of the air going past the stationary plane, the air density matters, the size and the shape of the wing matter. That's a big part of design. And then also what we call the angle of attack, which we'll use the symbol alpha for, which is the angle between the flow of the air and the chord line, just the line straight along the middle of the wing. And so we can change how much force we produce by pitching the plane up or keeping it level or even pitching it down. And so let's just think, if you guys want to think on your own, make a couple predictions, and then we're going to try it out with a simulation program. And so think about it for yourself for just a minute here while I get the simulation program up. How do you think that lift, the force that keeps the plane in the air, is going to be affected by angle of attack? Do you think with a higher, larger alpha, it's going to be more lift or less lift? And then how do you think that the lift will be affected by airspeed? Do you think going faster will be better, or would slower be better? Would slower create more lift? So think about that for just a second, and I'm going to get up my simulation software here to show you what we're going to try. Alrighty, so I'm going to put this website in the chat here for you. And everyone can go there. The only thing I will note is that it does not display correctly in Internet Explorer. So you're going to want to go in Chrome or Firefox or Safari. I think even the Microsoft Edge thing is fine. But Internet Explorer, it does have some problems with. So I'm in Chrome right now, which works great. And the website is this NASA foil sim program, and it should look something like this. So if everyone wants to take just a second and get there, then we can go ahead and try a couple of things. And this is something that's just freely available. So you can use this anytime if you bookmark this website. I really like to play with it. We won't use all the features today, but it's kind of fun to do basically a simulation of what we'd see for a wing during flight. All right, so if you're there, let's have everyone just start with the default settings. So it should look something like this. And we'll explore those two things. So we're going to explore our angle of attack, and we're going to explore the speed. And so the spots to look are this slider bar right here. This is angle-DEG for degrees. And then the spot that says lift up here. And you'll also see the lift plotted down below. So if everyone wants to just mess around with the angle of attack just a little bit and watch what happens to the lift, you can either slide the angle up to the right or down to the left. You'll see the picture adjust, and you'll see that lift value adjust. Try to figure out what is going to happen. What, does angle of attack going up make the lift go up, or does angle of attack going up make the lift go down? So I'll play with it a little bit too, but go ahead and try it on your own. And if you want to add a message in the chat, you can do that with what you found, or we'll just talk about it here in a minute. So if you just click to the right or the left, the right will take it up, the left will take it down. You can also slide if you want to make a more drastic change.